Minimizing expected loss in classification problem. In the previous lecture, we had seen how to use the minimizing misclassification rate approach. That is, in order to make a decision, we had two approaches. One is to minimize misclassification rate, and the second one to minimize expected loss. In the previous lecture, we saw the approach of minimizing misclassification rate. In this lecture, we are looking into the idea of minimizing expected loss for a classification problem. We are presently dealing with classification problem, and what if we use the minimizing expected loss approach instead of minimizing misclassification rate? Let us see this. So once you understand these two approaches, you'll be clear of where to apply what, that you will understand practically in what sort of a situation you should be going for misclassification rate approach, what sort of a situation you should be going for expected loss approach, right? So what happens is, sometimes simply minimizing this misclassification rate, that is if you have class C1 and C2, whenever you get an X, simply making sure that most of the X is rightly put into C1 or C2 won't really serve the purpose, because your problem statement may be such that your loss will be more dependent on some specific conditions. That is, sometimes some particular C1 class, missing out on this may be very risky, but on C2 class it may be okay to misclassify. There will be such conditions. For example, let us take the same example we took in the last two classes. That is, this is your border, you have cameras here, and these cameras are looking into people who are approaching in. Let us say there are few people approaching. What will you do? You have to take input X, which includes characteristics of these people. Let's say dressing, items in hand. Then what we had considered, bag in the shoulder, and body language. Anything, any few criteria. And our target is to identify the presence of enemy. That was our T. We had two classes, C1 and C2, in which C1 said it is an enemy and C2 said it is not an enemy, right? In this case, let us consider what happens if there is, let us say, one person approaching. He is actually not an enemy. Let us say not an enemy, not an enemy. But what did you do? You classified wrongly as enemy. That is, it was actually, this should have been in C2, which is not an enemy. But wrongly you classified as C1. What will happen? In this case, you have to send the troops to that area in order to make sure that this enemy won't attack. But what is the reality? In real, it is not an enemy, right? It was actually in C2, but your model wrongly mentioned it as C1. Because of that, you had to send the troops. So the loss you incurred is that extra loss that you had to send the troops unwantedly, right? This is the loss that you have in this case. But just consider the other case. What happens if it is actually an enemy? Actually, it is an enemy. That is, it should have been in C1 class, but you wrongly marked it as not enemy. This is your wrong marking, but you did as not enemy. What happens then? You should have sent the troops and protected the country, but you marked it as not enemy, because of which no troops were going there and these people got inside. So this is a huge security threat for you, because enemy who is coming in was wrongly identified as not enemy, and because of that you didn't send the troops, and these people got inside. So this is a big security threat. So in this particular problem, just think logically. This particular mistake that you made, in which you identified an enemy as not enemy, is way severe. This is very severe. But in the previous case, when it was not an enemy but you wrongly identified as enemy, that is okay. You can adjust this, right? The only issue is you had to send troops, which didn't cause much of an issue. It's just an extra burden of sending the troops. But the second one, in which it was actually enemy but you marked as not enemy, that is a very severe mistake, which means ideally in this sort of a problem, you should not be going for minimizing misclassification rate. Instead, what should you do? You should minimize expected loss, where this expected loss should include this criteria, that misclassification of the second type, in which you mark an enemy wrongly as not enemy, that is highly severe. And the first type of misclassification, it's okay, you can afford. This should be included in your expected loss. So let us see how you can include this criteria in your expected loss. This is the whole idea of this particular lecture. So till this point, you are clear that it is better to make lesser mistakes of the second type, that is putting an enemy as not enemy, even if you are doing this at the expense of the previous mistake. Okay. So first thing is we have to identify the loss function. So your input is X, right? Input is X. And let's say your true class is CK. We'll call it as CK. True class is CK. And let's say you assigned it to assigned class. Okay. This is the assigned class to which you assigned it. Assigned classes, let's say CJ. So you have an input X. This X you have to assign to one of the classes. The true class of this input is CK and the class that you assigned is CJ. So here K may be equal to J, K may not be equal to J. Okay, we'll consider all the cases. J is the class to which you assigned. It may or may not be K, but K is the true class. Okay, this is the scenario. So in this case, what is the loss incurred? Let's say loss is LKJ. So LKJ is the loss incurred if true class is K and assigned class is J. So what would you ideally do? If K is equal to J, in that case you would put LKJ equal to 0, because in that case there is no loss. You are actually assigning it into the correct class. For the wrong class, what can you do? Here, because you have a value of loss LKJ, you can manipulate this value such that loss is very high for one particular misclassification and loss is moderate for some other misclassification, right? So let us put this in the matrix so that it will be easier to understand. So let us say this is my matrix. Okay, this is my matrix. In this matrix, I'll mark true class here. So this is the true class. Okay, true class. True classes are enemy, not enemy. There are two classes. And true, what is true class? True class is the class to which it actually belongs. And here I'll put assigned class, or I'll simply write our class. Okay, our class is in this axis. Here you have enemy and not enemy. So both these are the classes we have assigned. That is what I have marked as our. That is what we have marked. These two are the true classes. Okay, this enemy, not enemy, these are the true classes. This enemy and not enemy, these are what we have assigned. So if it is truly enemy and we marked as enemy, in that case this is the loss matrix. Okay, this is your loss matrix. So if it is actually enemy and you marked as enemy, loss should be 0 here, right? Similarly, if it is not enemy and you marked as not enemy, this should also be 0, no loss there. If it is, let us say, not enemy but you marked as enemy, let's say here loss is 1. Okay, it is not an enemy but you marked it as enemy. But what about the fourth case, this one, in which it is actually enemy but you marked as not enemy? Here we discussed that loss should be very high. So what you can do, you can put a very large number here. Let's say I am putting 1000 here, which means if I do this misclassification in which it is actually enemy but you are marking as not enemy, here my loss is very high, loss is 1000. But in other cases, if it is correct class, I am putting loss of 0 and wrong class, I am putting loss of 1, right? So this loss matrix helps me to identify which particular misclassification is of high severity. What is the next step? I want to minimize the loss. I want to minimize loss. So how will I minimize loss? I have to first of all identify what is the total loss incurred. What is the total loss? Expected loss. So the total loss, how do I find it? I have to check the condition of my assigning this point to each of these class, and for each of that class I have to calculate the loss and I have to add it up, and I have to see under what condition can I have the loss as the least. Okay. So if I add up all the terms, summation over all k, what is k? K is the true class, this one. And summation over all j, what is j? J is the class we are assigning, this one. Okay. So whatever are here, these are j, whatever are here, these are k. So summation over all k, summation over all j. What are you going to sum? What is the term? Lkj into probability of, right, x element of class k, that is ck, and sorry, x element of, let's say, rk, that is the region k, which means it is ideally of kth region, but you are wrongly or correctly, whatever it be, assigning it into cj. So if j equal to k, it is correct assignment, and if j not equal to k, it is wrong assignment, right? So I put j and k interchangeably. Okay, region should be j and this should be k, right? So rj and class is ck. Okay, so let this be. And how do I understand this term, x element of rj and ck, which means x is actually belonging to the class rj, but I am putting it into the class ck. This can be written as how? Instead of this, let me rub this off, and instead of this term, I can write it as integral over the area rj. What I can do? P of x ck dx. What will this give me? Over the area, over the region rj, if I have assigned it into class ck, that is what it will give me. So that is same as this. So this part I will substitute with that. Instead of this, I'll use integral over region rj lkj into p of x ck dx, right? So this is the total loss that I want to minimize. So here my whole aim is to minimize this term, expected loss. If I minimize the expected loss, then my work is done. Just to show you how this loss term affects the whole thing. Previously, in terms of misclassification rate, we were simply looking at as probabilities. This time we have this loss term, and I'll show you how this loss term is affecting. Let us say I'm considering a case in which actually it is enemy, but you're putting as not enemy. In that case, let us say your model is saying there is 10% probability that is it is actually an enemy, and 90% probability that it is not an enemy. Let's say this is what your model found. In this particular case, if I put these numbers into it, 10% probability means 0.1, 90% probability means 0.9. With 0.9, I am saying that it is not an enemy, right? But in case it is an enemy, what is the loss? 1000 is the loss, right? And let us say for this 1000 loss, even if it is a 10% probability, which in which we are saying not an enemy, but it is actually it is an enemy, that 10% loss will give a total value of 100, right? But what about this 90% value? This 90%, even if it is considering that it is a misclassification, it will only contribute as 0.9 into 1, because our loss here is only 1. So this will give a total value of 0.9, while the other one will give total value of 100. 100 is the error cost because of this, even if it is a 10% thing. That is, if your model is thinking there is only 10% probability that it is actually an enemy, but you are going to mark it wrongly as not an enemy, even that 10% has a much higher weightage, that is more than 100x weightage of a 90% probability, which says it may actually be not an enemy, but you are marking it as enemy. So what did you understand from this? From this, you need to understand that because of this high value of loss function, loss value that you put on one particular type of misclassification, your model will put its best efforts to make sure that even if there is a 1% probability that it can be an enemy, it will make sure that it will mark as enemy only. It will never mark as not enemy. Only when it is 99.9% sure that it is not an enemy, then only it will mark as not an enemy. So in this particular case, this is the logic that you used. So from this, what can we conclude? This is a loss matrix. So what can we finally conclude from this? Our expectation, we found the expectation, right? So we have to find a region. Using this logic, by minimizing error, we have to find the region Rj to which you have to assign. How will you assign Rj? You will find that particular Rj for which you will minimize the sum, that is sum over all k lkj, right, into probability of x ck dx, right? You want to try to minimize this for each x, for all of the x. For each x, you will do this thing. You will try to minimize this value. And here, to assign this to any particular x, what will you do? You have to find this probability and this loss function. And how will you find this? What is it that you have to find? P of x ck, this can be written as P of ck given x into P of x. So once you know the posterior P of ck given x, for calculating this is easy, right? If you know the posterior, then you can easily calculate this. So this can also be said as, whenever you get a new x, whenever you get a new value of x, you have to assign it into that particular class which minimizes this sum, that is sum over all k lkj P of ck given x. So here I am only considering the posterior instead of this complete joint probability distribution, because posterior will do it because P of x is common for all the classes. So posterior is what is different for different classes. So if you take just this term and for each of the input value of x, you consider that particular class that will minimize this summation over for each of them loss into posterior. If it will minimize this summation, that is the class you have to assign. Just to show you the graphical representation idea that we discussed in the last class, how will the same graph look in case of minimizing expected loss criteria? Previously we saw a graph in case of minimizing misclassification rate criteria. Here, if it is this particular criteria of minimizing expected loss, the same graph will instead look like this. We draw a graph of something like this. We had one as P of xc1 and the other distribution was P of xc2, and we said xc1 looked something like this, right? If you remember, something like this. And we had P of xc2, this is P of xc1. xc2, it looked something like this, right? Something like this. This was xc2. So okay, I'll extend this a bit here. Okay, this was our P of xc2. Then what did we find in the last lecture? In last lecture we found that the decision boundary for this ideally should be somewhere here, because this will minimize misclassification, right? This is what we saw, and according to this, this should be region R1, this should be, all the points here should be in region R2. This time we are using minimizing expected loss criteria, where what do you want to make sure? You have to make sure that if it is in C1 class, that is enemy class, it should surely be assigned as an enemy, which means this same the decision border, this will get shifted to the right side. Instead of here, this decision border would come somewhere over here. I think it will be somewhere over here. Why will this decision border be shifted to this point? Because if it is this point, then whatever is in this side, this will be marked as region R2. And whatever is in this side, all this will be marked as R1. So as we previously said, this decision comes at the expense of marking some of those which are actually not an enemy as enemy, and which is that area that is denoted by this area. That is, if you see this area is actually not an enemy, or or it can be enemy as well in here, and this part is not an enemy, surely not an enemy, but you are still classifying it as enemy because you cannot afford the mistake that you cause here, right? In this place you are saying you are sometimes it can be an enemy, right? And still you may mark it as not an enemy because it is of region R2. So you can't afford more of these mistakes. So in order to compensate that, you are okay to mark some of your C2 class as C1. Because even after incurring that loss, your total expected loss will be lesser. This is the whole idea. So depending on your case, depending on your requirement, you need to identify whether you have to use minimizing misclassification rate criteria or the minimizing expected loss criteria. In case you are using this minimizing expected loss criteria, in this case you have to use good amount of your knowledge, your problem knowledge, in order to identify the right loss matrix, because the loss matrix decides a lot of things here. If you have the right loss matrix, you put the right values of loss for each misclassification, then your model would work perfectly.